Okay, so let's work this problem. We'll determine the displacement at C, which is right here in the middle, due to an applied point load at 16. Very similar to the problem we just worked as an example, but we'll go through it a little more slowly. We have a value for I and a value for E. And we've talked before about direct integration for this kind of problem would be a little challenging, and probably you would end up with 4 equations in the 4 integration constants, 2 for this section, 2 for this section, and that would take a little time to solve. Not impossible, but a little tedious. Conjugate beam, this would be a good problem for conjugate beam. So this might be, since we've done some conjugate beam problems in the last week, you've kind of got that in your brain. So as we do the virtual work, you can kind of do a little compare and contrast and see which one you like better. As we move towards the exam, I'll just give you this problem, or a problem like this, and I'll just give it just like that. I won't tell you what method to use. So part of the exam will be you choosing which method that we've learned is probably best suited for the job. Right now, I would say direct integration would not be the best choice. Conjugate beam and or the virtual work would be better. So let's start with virtual work. So the first thing I need to do is be able to write the moment equations for the actual load here, the real load system. So I'm going to assume that I have a reaction at A and also one at D, and I'm going to find those reactions to help me find the internal moment. So I'll come over here and I will sum the moments at D, make sure it's in equilibrium. So about D, I'm going to find basically my AY reaction. So looking at the only force applied, in this case the 16 kip force, it creates what kind of moment about D using the right-hand rule? Positive. So that'll be a force of 16 kips, and the distance from D to B looks like 30 feet. And then the AY reaction is going to create negative moment, and that will have a force of AY and a moment arm of 40 feet. So we should be able to calculate AY. It looks like it's 12. Does that sound right?
Yes.
And just to finish this up, we can sum forces in the Y direction. I'm assuming up is positive. So I have AY and DY, they're both up, so those are positive. And I had the 16 kip force acting down, so I'll consider that to be negative. And since I know AY, I can plug it in here. It looks like DY is going to be 4. Okay? So now I want to find, I'll call it my real moments. In that case, can I write a single moment expression for the whole structure? No, right? I have to go from 0 to 10, that would be one moment, and then from 10 to 40. So let's think about the 0 to 10 first. I'll make a cut here. I'll pull this right of there. Do you want to look at the left side or the right side? Yeah, I think the left side is going to be a lot easier. So let's do that first. So for my real moment, I'm looking for an expression that's going to be valid from 0 to 10. And looking at the left side, I have my reaction AY, which we solved for already, which was 12 kips. And I'm only considering moment now, so there's the real moment caused by that. And I'm cutting it some distance x. So if I sum moments at the cut, make sure it's equal to 0, what do I get? Well, I have the internal moment, that's positive. I have the moment due to the 12 kip force, that's creating negative moment with the moment arm of x. So it looks like my real moment is equal to 12x. And that's valid from 0 to 10. Any questions about that? So now we're going to cut the structure somewhere here between 10 and 40. So if I cut it here, you have to decide whether you want to work the left side or the right side. And I think the right side is going to be easy. So this would be valid from 10 to 40. And in that case, my free body diagram will be the right segment of the beam. At the right edge, we have dy, which is positive up, and that's 4 kips. We have the internal moment, m, and I have the distance x up to the cut, and that leaves the right-hand side segment, which would be the total length minus x. The total length is 40, so that little piece will be 40 minus x. And when I sum moments about this cut surface and make sure it's in equilibrium, well, what do I get? I'm using right-hand rule, so my moment here is what? Positive or negative? Negative. And the 4 kip load creates what kind of moment about the cut? Positive or negative? Positive. So I'll have 4 kips times a moment arm of 40 minus x. So when you solve for the moment there, you get 4 times 40 minus x. I've left off my units here, but remember my units are going to be kip feet on both these expressions. So we have our real moment expression. Now we can check these before we move on. Let's do a quick check. Do I know anything about the moment in this beam? Well, what's the moment at A? 0. So let's find the equation that includes A, which would be this one, 0 to 10. And that's at x equals 0. If I plug in x equals 0, what does my equation tell me it is? It's 0. That works. I also know the moment where? At the other end. That's at x equal 40. So I have to use the equation that's valid in that range. And if you plug in x equal 40, hey, what do you know? That works. Now, what should be the moment at the point they share, 10? I don't know what it'll be, but it shouldn't change as I go from the left side to the right side. So I'll evaluate the moment at 10 here. What do I get? Looks like I get 120. And I evaluate the moment at 10 here. 40 minus 10 is 30. 30 times 4, 120. So they match. So I'll just write over here to remind you that I did check that the moment at x equals 0 is 0. That's true. We also know that the moment at x equal 40 in this problem should be 0, right? And we check that. And also we know that really the moment from the first segment at x equal 10, whatever it is, should equal the moment from the second segment at x equal 10. And we just checked that. That was 120. So lots of green checks. So I feel pretty comfortable about the moment expression being correct. Okay. Now we just have to do it again, but for the virtual beam. So let's see what our virtual beam would look like. So I'm saying you're not quite halfway through. You've got the real moments. You're going to have to get the virtual moments. And to finish the problem off, you have to assemble them correctly so that you can write the virtual work expression. So what would our virtual beam look like? Well, the first thing we do is the geometry is the same, right? The Supports are the same. This is not conjugate beam. I don't have to do any kind of mapping. But what do? I take the real forces off, and now I put my virtual force on this beam. Where do I put it? Well, the problem wants to displace it at C. Where's C? Right in the middle. So that's where I put my virtual force. Now I have to decide whether I think the displacement's going to be down or up. Now, if you don't like that, always assume your virtual force is up, positive. And when you compute it and you get a negative value, then you know it's actually down. I'll let you guys decide which way do you want to go, up or down. Up. So there's my virtual force of 1. It's right in the middle, so this becomes 20 feet and 20 feet. Can I write one expression that's valid for this beam? No. So I have to write a virtual moment that's good from where? 0 to 20, and then another one from 20 to 40. You guys see that? So then I'll need to calculate the reactions to this. AY and DY. These aren't too challenging. You can probably already guess what they're going to be. But I'll sum moments about D and make sure it's in equilibrium. And when I do that, my virtual force is creating negative bending moment, force of 1, distance of 20. And my reaction is also creating negative reaction of 40. So in this case, AY is going to be negative 1/2. It's half the total force, and since the force is up, it's down. That seems reasonable. And then we'll go ahead and quickly sum forces in the y direction, make sure that's in equilibrium. I've chosen to use up as my sign convention, so both AY and DY act up. And my load is also up. So I plug in AY here, you find that DY is also negative 1/2. That's not a surprising result. So now I got to develop the virtual moments for this system. So I'm going to cut it here. So the first one will be valid from 0 to 20. So I cut the structure here, and you have to decide whether you want to work the left side or the right side. What do you want? Left. So I will cut that at some distance x from the left side. We know that the reaction is down 1/2. Right? We found that. And now we're looking for that's the lowercase m, the virtual moment. So when I sum moments at the cut here and make sure it's in equilibrium, well, what do I get? Well, this is positive with my sign convention, so there's the virtual moment. This is also positive, so it would be a force of 1/2 times the distance x, so it looks like the virtual moment is equal to minus x over 2. I think I'm going to go back and double line those so they show up a little better on the slide. And then I have to do it again, right? The next expression will be from 20 to 40. So I'm going to cut the structure here, and you have to decide right side, left side. I said that backwards. Yeah. Left side, right side, right side. So if I cut that structure to the right, that means I need to put dy. We calculated dy and found it to be down value of 1/2. So from the left edge, I'm cutting it at some arbitrary distance x, and that gives me the remaining length of the segment to be 40 minus x. And then really all I'm looking for at the cut is the virtual moment. So again, if we sum moments at the cut, make sure it's in equilibrium, well, what do we get? From right-hand rule, this becomes a negative moment. This 1/2 acting down also creates negative moment, and that'll be a force of 1/2 times a distance of 40 minus x. And solve for the moment, you get minus 1/2 40 minus x. So we finally got all the pieces that we need to solve the problem. But I've run out of paper. I got to find another piece of paper. Bring a blank. Does anybody have a white blank piece of paper that I can borrow? I'll pay back with interest. Oh. So let me slip this up here, and we'll write that the displacement at C is going to be the integral over the length, 0 to 40, of the real moment times the virtual moment divided by EI. That's our general expression. Now, how are we going to break up our interval 0 to 40 to accommodate our different equations? Well, if you look at just the real moment, you can see I've got two already. I've got to go from 0 to 10 and then from 10 to 40. If you go down here and include the virtual ones, well, this one is good from 0 to 10, right? But it's also good from 10 to 20. So I'm going to have to break that up, right? Because this one doesn't go from, this one goes 0 to 20, so you have to switch the moment, the real moment, to accommodate this guy from 0 to 20. Now from 20 to 40, this one's good, and this one's good. So you're going to have to break it up into 3 pieces, right? So what we're going to have is the integral from 0 to 10 of the real moment, which is 12x, times the virtual moment, which is negative x over 2. I should have factored my EI out, but I didn't, so I'll just have to do it this way right now. And then this is still good till 20, but now this one kicks in from 10 to 20. So I'm going to have the integral from 10 to 20. Now this is my real moment. 40 times 40 minus x times my virtual moment minus x over 2 divided by EI dx. And then finally, they're both valid from 20 to 40. So this is still the real moment from 20 to 40, 4 times 40 minus x. But the virtual moment now becomes this, 1/2 40 minus x. And then divide that by EI and integrate that. You can see how that would be very troublesome to pull off in an exam. There's countless places in this next expression where you can make errors. And to be honest, I'm really not that concerned that you can integrate a polynomial and evaluate it. I think you've probably already been through that. That's not the purpose of this course. So for me, that's a good place to stop. That's all I would require you to do. You've written in review, you've written the real moment expressions and identified the range where they're valid. You've established your virtual beam and the correct loading, and you found those moments, and then you've pieced them together so that you've accounted for the energy for the whole structure. Now what I'm going to do is I'll go back to my office and I'll do all that, and I'll fill this in. So you can see it when I post it online. You can actually see the numerical value if you want. But I'm going to draw a big red line here and say that's good enough for the exam, especially on one like that. This one down here would be very tedious to evaluate. Questions about that? Yeah.
Yeah, can you explain again how you decided what list to use?
Well, you have to match them where they're common, right? So, see, this is good from 0 to 10, right? And this one is good from 0, also 0 to 10. So I can match that up. That's how I got the two here, 0 to 10. But at 20, what happens? Or I'm sorry, at 10, what happens? I have to switch to a new moment, right? But I can't go from 20 to 40 because my virtual moment's only good from 0 to 20. So I got to stop at 20 and then shift to this one from 20 to 40. Maybe I can do this. Maybe you can see it better if I do this. So that term right there, right? That's the real moment from section 1, which is only valid from 0 to 10, right? You'll notice that this one and this one are the same. That's the real moment in section 2. And it's valid from 0 to 40. See that? And if I did something similar, which I'm probably going to run out of colors here, you'll notice that this and this, well, that's the same moment, right? If I connect those two, that's the virtual moment. And it's valid from 0 to 20. And then it changes over here. And that one's valid from 20 to 40. So you have to make sure that you put the pieces together correctly. I don't know if that helps me. That looks like some kind of weird tree of life diagram. Okay, so this video's lasted almost 23 minutes. Obviously, that's way too long. And we've talked and answered questions, so that's way too long for an exam. So there's no way I'd probably ask you to finish that off as requirement. So this is good enough for me right there. We'll minus all the colors. Anybody else have any questions? Yeah.
Do we have to draw those cuts?
I think it's important that you always include your free body diagram when you're coming up with these expressions. Because if these are wrong and I can't track it back, I have no idea where you made a mistake.
So like on the bottom one, if you know...
If you just want to say AY and DY from this are -1, that's not as critical. If you get it wrong, it is critical, right?
No,
if you see it clearly...
If you know AY is -1/2, and you know the V is -1/2, so M is just integrate.
Well, here's what will happen. If you draw this, and then you suddenly just write these two things down, and they're correct, I cannot complain. If they're incorrect, I can complain. I can complain by giving you no points. All right? I don't say show your work, but I think it's important that you do. Because I don't want you to potentially be accused of looking over at your neighbor's paper and spotting a -x/2 and just writing it down.
What if I said AY equals -1/2, so V equals -1/2, M equals integral of V?
Integral of what?
Integral of 1/2. Since M is you integrate V to get M.
What you're saying is you're integrating the shear equation to get the moment equation.
Right.
Yeah, well, you can do that, but you have to be careful. I'm not sure if what you just said will work every time for every situation. It'll probably work for the virtual being, but in general, that shorthand can get you in trouble if you don't account for everything. It's real easy here because it's just a single load, right? And it's probably always going to look like this, with some distance, with the distance changing and maybe the reactions changing, right? I move this point around, these reactions will change, but the form will be the same. You could. I mean, if you're pinched for time, and it's the last problem, and you just got to get something done because I've said 10 minutes and you haven't finished, then yeah, go for it. But if not, I would be as explicit as possible. Show me everything you've got. I'm a little more forgiving. Like if you were to do all this detail and like say maybe right here you said a half, but somehow it became 1/3 there, like just in the heat of the moment, I'd be probably fairly forgiving of that. If you just had the 1/3 in your head and this just says negative x over 3, I'd probably be not very forgiving of that. So there is some advantage, I think. Okay.